Our last presenter for this session is Thompson from Harvard University. His field is geophysics, and his advisor is Brendan Mead. He did his practicum at Oak Ridge National Laboratory in 2015. So today he'll be discussing earthquakes, topography, and the shallow slip deficit inference.
Thank you. Can you hear me? All set? So a lot of you are physicists. You've heard about the physicist that's thinking about a cow and models it as a sphere. So as geophysicists, for decades, we've been thinking about the Earth, and occasionally we model it as a sphere, but most of the time we're interested in a small area, so we model it as a plane. We think of it as flat. Well, most of you probably know the Earth is not flat. And when we're trying to progress science from qualitative statements into quantitative predictions, we want to have accurate, good geometries for the things that we're talking about, in this case, earthquakes. So I'm looking at this question of when and how do faults slip, and I'm trying to answer some questions about this in a quantitative way that's moving a little bit of a step beyond the qualitative statements we've been making for 50 years. So just to introduce people to the subject, let's think about this red line here. You can think about this is a map view looking down on the surface of the Earth. This red line is the intersection of a plane that we call a fault that's going deep into the Earth, and it's a surface that things move past each other. You've got this plate on one side, say, you could think of this as California. This is moving south, and this is the Pacific moving north, and they slide past each other on this fault. But most of the time, that fault is completely stuck. Nothing's moving. So if we go over here, I have this plot of time, just a schematic, time versus fault slip. So slip is how much the fault is moved past. The two sides have moved past each other. Most of the time, the fault is locked, these places where fault slip is not increasing with time. Occasionally, you get creep behavior. So some parts of the world, faults creep more than others. At some times, certain faults will creep and other times they will not. Essentially, that means that the fault is moving really slowly and it's releasing all that energy that's built up. We really like creep because that means that the fault is moving without damaging anything. The bad thing that we have is earthquakes. That's when the fault slips a whole lot really fast. So a big earthquake might take a minute for the fault to move 1 or 5 meters. And that creates large seismic waves that damage buildings, and we don't like that. After that, sometimes in a lot of places, you'll get post-seismic behavior. What that means is just that after an earthquake, the fault's been disrupted. The state of the frictional behavior on that fault is a little different than it normally is. And so it moves quicker than it might normally, or if it's normally locked, it still moves for maybe 1 to 10 years after an earthquake. So for some fault in the world, we often want to answer the question, which of these different modes of behavior take up more or less slip, and when do they happen? The reason we care is that the most important reason is how much of that slip, how much of that energy is released during earthquakes. So there's a question that's been lingering in the community for a while called the shallow slip deficit question. And I've got this plot over here, depth versus normalized moment per unit rupture length. You can think of that really simply as how much did the fault slip at certain depths. And so for several different earthquakes here, ones in California, Turkey, Pakistan, or actually Iran, I think. You see this pattern where there's much less slip at shallow depths and deeper depths, and quite a lot in these mid-crustal depths of 2 to 6 kilometers. So one thing to realize here, that would be a big deal because it means that a lot of the energy that's building up on faults in the shallowest portions, the most dangerous portions, the shallow parts create larger waves for cities that are right above them. They're closer. That would mean that a lot of that energy is not being released in earthquakes. That'd be a great thing. The other thing that I want to mention here is that we don't actually directly observe any of this. This is all inferred from surface measurements. We have GPS stations on the surface that measure how the Earth moves after an earthquake. And then we go through this whole inverse problem situation that a lot of you are probably familiar with to determine this slip pattern as a function of depth in this case, or maybe where you are in a map. And that inverse problem, the way we do it could be flawed. So this inference of a shallow slip deficit, maybe there's a real physical reason for it. Maybe it's a real signal. Or maybe it's a signal that's a result of doing an inverse problem in some imprecise way. In particular, when we're closest to the surface, that whole thing about treating the fault as a plane, that's where that's going to matter the most, because we're closest to that. We are closest in the inversion to that model error. Essentially, we have a model error. We're treating the Earth as flat, whereas we have mountains, we have valleys, we have canyons. And some of these earthquakes, like the Landers and Hector mine earthquakes, these are in Southern California, where you have substantial topography. The San Bernardinos, if you're from the area, it go up to 3,000 meters almost. So I'm going to start with a really simple kind of synthetic inverse problem, asking, I'll flip ahead really quick, asking if we add this hill above a fault, this is cross-section now, so this is depth and then along the fault. If we add this hill above the fault, how does it affect a synthetic inversion? So I'm going to start with a set of motions along the fault, propagate that with a forward model to the set of what we might observe in terms of displacements on the Earth's surface. So that then, this is map view again. This is showing blue is motion to the left or maybe west. Red is motion to the right. So you can see that you have this relative motion across the fault. And then I'm going to invert that using a different model, a model that has no topography, and ask what fault slip do we infer? So essentially, this is asking the question of what error do we introduce by ignoring that topography? What is the result of this model error? So what I'm showing here is that result. So again, we have the fault discretized into a bunch of triangles. As a function of depth, the fault does not actually extend to the surface in this case. And then in the first panel, I'm essentially inverting with the correct model, the model that produced our observations at the surface of the Earth. And what I get back is a uniform slip distribution, or almost uniform. There's some effect due to regularizing. If you're familiar with doing inverse problems, often you have to kind of tame the system in a way. And so we do lose some signal, but for the most part, we get back the uniform slip distribution that we put in. So that's good. Now, if we then invert without topography, okay, over away from the hill, we're getting back a pretty uniform distribution. Over here, too, away from the hill. But under the hill, what you see is we get this artificial inferred slip deficit. This is exactly what I'm talking about in terms of a shallow slip deficit. This is a part of the fault where, even though in reality it slipped just as much as the rest of the fault, in our inversion, we're inferring that it slipped almost none in the center of this. It's almost 0 meters as opposed to 4. With a gradient, the closer you get to that hill, So what that's saying is that, at least in this simplified problem, I'm going to move on to some real-world examples. Ignoring topography creates an artificial shallow slip deficit. So let's talk about the Wenchuan earthquake. So this is a major earthquake in an area of steep topography in western China at the edge of the Tibetan Plateau. So I'm showing all these red arrows are the motions observed on the surface using GPS stations after the earthquake. Then this is a fault mesh inferred from all sorts of different data. This is, again, looking at the model that we've put together. So you can see the topography in the Tibetan Plateau on the right here, and then the shallow basin to the left with the fault cutting in between. And you can even see we have earth curvature. So this is trying to be as geometrically accurate as we can. What we find is I'm showing map view here. So this is longitude, latitude. What we find is a dominantly shallow slip earthquake. So you see large amounts of slip in this section of the fault near the surface. I'm going to come back to this in a few slides and compare to what we've seen before from other inversions. So then the second place I'm going to look at is Southern California. This is about 100 miles east of LA, out in the Mojave Desert. The Landers earthquake in 1992. So this is a plot of kind of model-inferred motion on the surface of the Earth. So longitude, latitude, north is up. The black line is the fault intersecting the surface of the Earth. You can see on the west side of the fault, the motions were to the north. On the east side of the fault, the motions were to the south. I'm going to do the same sort of inversion here. So ask, where is the slip on the fault as a result of those GPS observations? And you can see, just looking at these different segments, it was actually a multi-segment fault, and there's a lot of interesting discussions about how the behavior jumps from segment to segment. You can see eyeballing it doesn't look like there's a shallow slip deficit. And then over here, I'm plotting how much slip there was as a function of depth. Okay, yeah, we can confirm our eyeball observation. There's actually a bit more slip in the shallowest parts. So let's compare this to what people have inferred before. So if we look at this plot over here, there's this Fialco 2005 paper, which is which is a well-known slip inversion for the Landers earthquake. You can see that in that paper, compared to what I've produced, which is in red, you can see there's a lot more slip at depth and a lot less slip in the shallow portions of the fault. Similarly, with the Wenchuan earthquake in China, you can see there's a lot more slip at depth than near the surface. So in both these cases, essentially, by adding topography to our models, our inferred slip moves from deeper portions of the fault to shallower portions of the fault. So in a way, this is saying our previous inferences about where slip happened, where earthquakes slip, could be flawed as a result of that assumption that the Earth is flat. And really, this idea, maybe the shallowest parts of faults slip less, well, maybe that was a result of the way we were inferring these values. And that's important, because it means that shallow parts of faults may slip just as much as the deep parts. And really, our seismic hazard, the thing that we really care about at the end of the day, is larger than we might have said it was 5 years ago. One of the lessons from this, I think, that's really interesting and kind of covers a broad portion of computational science, is this idea that inverse problems amplify errors. If you have some model error in your forward model, the inversion process naturally amplifies that, and your inverse problem will be much more flawed as a result of that error than your forward problem. So all of this is part of my PhD in general has been an examination of okay, almost done. An examination of how geometry affects earthquakes in a variety of different situations, and it's been based on some boundary element tools that I've been developing specifically for earthquake science. I'm using techniques some of you may have heard of called like fast multipole methods. There's some really interesting integration problems here. It's been fun. I wasn't focusing on that here so much, but if you ever want to talk about that, we can do lots of huge problems, and it's really enjoyable stuff. Anyways, so just to finish up, I think that there have been some previous explanations for this inference of shallow slip deficit. Maybe there's motion that's not on the fault. You have bending in the earth. Or maybe there's motion at other points in the earthquake cycle. You have more creep on the fault, or there's more post-seismic deformation. I'm proposing a new explanation for this, which is essentially that in some earthquakes, the shallow slip deficit is an artifact of ignoring the topography in the region. Thank you.